my pressure entities Sunita Sarvati. So note her log time from background we have both at type and manual. So backend shows the database person and now she has more for machine learning person and she's going to tell us about some fun machine learning stuff.
Okay. So standard machine learning task on which there is more than 50 years of research is to predict one of a fixed set of class labels given some input x, and typically the x is assumed to be a fixed dimension. But of course when you apply machine learning on complex environments such as this, the single prediction model is awfully inadequate. So there is a lot of interest in amongst current machine learning researchers to predict output which is not just one of a fixed set of class labels, but rather a collection of, if you will, class labels. So you can think of your output as a vector of predictions. And the vector length is not fixed, depends on your input x. And the input x is also not a record like what we had in the old days. And in fact, the output may not just be thought of as a vector, it can be any arbitrary structure. For example, you could be predicting an alignment of two schemas or of two sentences in two different languages, which tells you the correspondence in the words between the two languages. Or you could be given as input a sentence and you could be predicting a parse tree of that sentence. So essentially, this framework looks pretty powerful and also somewhat intimidating, right? In the sense that the space could in fact be infinite. So how do you learn, right? In the old days, you knew how to classify things, whereas here you have a possibly infinite space. So how do you get your mind around it? So the first abstraction which enables you to tackle the problem is to define what is called a feature vector. So which feature vector is defined jointly on an input x output y pair, and the set of possible features for any given problem instance is fixed. So you have some capital K features. And then the model is defined just in terms of the K weights. These are real values which are attached with each feature. And then you can define for each possible output y over an input x a scoring function. So we are going to use SXY to denote a score of predicting output y for any given input x. And then the prediction problem, the classification problem becomes that of finding the highest scoring y. So your prediction problem is to find this y star for which the score is maximum. Now this could be challenging because typically for the structured problems, the space of possible y's is very large. So that is the next abstraction which helps make this feasible and practical, and that is the decomposability of the feature vector. Even though we started off defining the feature vector jointly over any input x and output y pair, in practice the feature vector would decompose over smaller parts of y. So although you would have to maybe predict, say, a set of 1 million class labels, in practice, the feature vector would decompose over much smaller subset of these 1 million labels, perhaps 2 or 3 of them. And corresponding to different ways of defining the feature vector and different methods of decomposing that feature vector, you have to design different inference algorithms. These are also popularly known as the map inference algorithms for solving the prediction problem. And this is one challenge. This is one problem which occupies machine learning researchers a lot, how to design the inference problem. The second is, of course, the training problem. During training, we assume that for any input x, we have one correct y. And you are given n of this correct input-output pairs, and you have to come up with the best w. So in this talk, we will see examples of both an interesting prediction problem and issues that arise when you try to train the w's, in terms of efficiency and generalizability for structured learning tasks. And my application, and also for many of the machine learning researchers, one big motivating application was information extraction. And we'll see how different scenarios of information extraction give rise to different kinds of structures that you have to predict. And for each of them, either we can fall back on existing inference algorithms, or in one case, we have to actually think about new inference algorithms. So this is what we'll be doing in the rest of the talk. So we'll be seeing structured models applied in information extraction, and we will give an example of an inference algorithm and address some issues during training structure models. So actually this is like part of really ongoing active research in machine learning on structured learning. So in information extraction, the most classical setting of statistical approach of information extraction, you are given an input sentence. And in the most common approach, you actually think of this input sentence as being consisting of the set of tokens which comprise that sentence. So in this input sentence, you are given 9 words. And the extraction task is that of finding from this input sentence your structured fields. So that is the top level task. And in machine learning, when you apply the structured approach, you break it up into the task of predicting for each word a label. And the label would be one of the structured types that you're interested in. So suppose if you're interested in extracting from sentences which appear in blogs, whether there are book titles and people names mentioned in blogs, then you would be interested in maybe predicting whether a word is part of a book title or not, or whether it's part of an author or not, or if it's none of the above. So now actually if you were to reduce it to standard multi-class prediction problem, you could want to predict for each of this ith word one of these 3 possible class labels. But it turns out that you gain much more by recognizing that actually these 9 predictions are not independent predictions. You do much better by capturing the correlation in the prediction of adjacent words. But also, other thing people have found out over the years is that it's not necessary to capture the correlation of arbitrary other words. It's just enough to capture the dependency of adjacent words, or maybe of 2 adjacent words. But let's just consider one adjacency for the moment. And that directly gives us a way of decomposing this otherwise daunting feature vector which you would define over your input x and your vector of 9 outputs. Instead of that, now we can decompose it into a feature vector which just involves pairs of adjacent y's, the ith y that you have to predict and the I minus 1th y, and then any other property that you want to capture of the word around the ith word in your input sentence x. So with this form of decomposition of the feature vector, and for this output structure, which is a chain of prediction, you can actually solve the inference problem very easily using this well-known Viterbi algorithm. This is what was used, for example, in HMM inference, in CRF inference, and it's very well known. And you have a trivial linear time algorithm for solving this problem. Now in information extraction, this is some work that I did in 2004, where we claimed that actually this classical method of word labeling for information extraction is inadequate when you want to exploit more powerful features. And in fact, you might be better off thinking of extraction as a segmentation problem. So you take the same input x of 9 words, and instead of your output being just a label assignment to each of the words, you think of your output as a segmentation of the sentence, where each segment is the entire entity that you're after. So instead of trying to label each word as whether it's a title word or not, you find the entire segment which comprises a book title. Similarly over there, you try to find this segment which comprises the author names, and because you don't know the length of entities in advance, this is actually now a much larger output space. You have to simultaneously break up your sentences into segments where each segment comprises an entity that you're after, and then of course you have to assign a label to the entity. So now the output y is not a vector of labels, but rather a segmentation. And in this case also, it is adequate to define your feature vector over, so suppose if your output, in your output you predict p segments, and note that even for a fixed input n, the number of segments is variable. But for any given set of p segments, you can say that the feature vector decomposes over the segment, the jth segment that you're predicting, any properties around the jth segment, and just the label of the previous segment. So that's why it's actually also called a semi-Markov model. So, normally, Markov models are what are commonly used, but semi-Markov model turns out to be quite useful, not just in information extraction, even for many of the speech recognition tasks, semi-Markov models are useful. And in this case, the previous Viterbi algorithm can be extended through a kind of 2 nested loops, and you can find the optimal segmentation, the map output in quadratic time. So here also we can fall back on an existing inference algorithm. Now I'll present a third instance of applying structured learning to information extraction, where we had to come up with more interesting inference algorithm. So this is when you want to do information extraction, not for each sentence in isolation, as I presented in the first scenario, but rather over a collection of sentences. So here is an example of, say, 3 sentences, and say I am interested in identifying from the collection of sentences that I am shown, say in a document, all occurrences of company names and people names and organization names. This is actually a classical NLP extraction task which comes up in Muck and ACE and all that. Now, very often, when people are shown examples of information extraction, the moment you see proper nouns which you relate to, then you think of extraction for a human being as a very trivial task. So just to obfuscate that, I am replacing words with some placeholder. So why is very lively. When you think, when you see a sentence like this and you are asked to find out for each of these words, whether it is part of a location name, a person name, or a organization name, then in a sentence like this, why, you don't know whether it refers to a person name or an organization name. But on the other hand, if you see another sentence which says that Mr. X lives in Y, then it becomes very clear, and particularly both of the sentences are one after the other in the same document, that Y perhaps is a location name. But it is, when you do statistical machine learning, you are not going to assert on anything as a hard and fast rule, because a third occurrence of Y actually may not be using Y in the same context as the first 2 occurrences. So here is a third sentence which says that X buys Y times daily. Now in this case, you would want to label Y times in this third occurrence of Y as part of an organization name. So basically for each prediction task, you have to take into account not only the context of that prediction in its linear occurrence in the sentence, but also across sentences you have to capture correlation. So now this is again a task of predicting a vector of labels, but the dependency amongst the predictions is a bit more complicated. So in the old case, you would just have dependency amongst adjacent labels and you could use Viterbi to find the optimal labeling. But now when you have links amongst words which are the same, and you want to kind of add a bias which says that all words which are linked through these cross edges tend to get the same label, then your task, your inference task actually becomes harder. So for this example, I have this one actually click corresponding to word X and this second click corresponding to word Y. Now the feature vector in this case decomposes in terms of 2 kinds of features. The first kind of features, they capture the dependency within a single chain of adjacent predictions. This is what you see over here. And the second kind of features, they capture the cross-chain predictions. So now I will, over the next 5-10 minutes, give you the inference algorithm that we had to come up with to solve this task. This actually turns out to be quite interesting, particularly when you look at the fact that this is the collective labeling problem, and many researchers in the past have tried to come up with information extraction scenarios using collective labeling, and they had to fall back on algorithms which basically thought of this prediction problem in the context of a Markov model. And when you think of it as a Markov model, it's a graphical model, and can you just use existing graphical model inference algorithm like belief propagation. So for example, in 2004, Buniske and Munu and actually also McCallum and his graduate student, they used message passing on this graph. Just normal belief propagation. You cannot solve this using exact inference because the graph gets very large. So you have to use approximate inference. And loopy belief propagation was one method which has been tried. Other researchers have used sampling or greedy local search, but none of them have guarantees. And what we did in this ICML 2007 paper was show that actually this graph has two interesting aspects which if exploited separately could give rise to much better algorithms. So the first observation is that if you, for example, could afford to ignore the dependency of adjacent predictions, and if you just looked at the edges which are across the different documents, then these edges have this property that they are associative, in the sense that they prefer adjacent, every edge it adds this bias that the nodes that it connects should get the same label. This arises in many other scenarios, like for example in social networks. We want to claim that friends of smokers are smokers. Similarly, neighbors of locations are locations. So when you have this special kind of graph, normally when your graph, for example, is a complete graph, and if your edges can take arbitrary kind of this scoring matrix, then the problem soon becomes NP complete. You cannot solve this in any tractable way. But for the special case of associative edges, people have shown that many existing algorithms can give you exact solution when the number of possible labels that each node can take is 2. So in the vision community, for example, Boykov in 1999 showed that a min-cut based formulation, you can take this graph and kind of redraw it a bit with the source and sink node, and use these associative edges to come up with edge weights. And then if you find min-cut in this graph, then the two ends will give you the set of nodes which should be labeled 0 and 1, and that is optimal. Then there was this very nice piece of work in 2005 by Kolmogorov and Wainwright, where they showed that even the vanilla belief propagation algorithm, which normally gives you no guarantees of optimality, will give you the exact solution provided you do message passing in a particular stylized way, like tree-based message passing, and you will get the optimal solution when you have to predict 2 labels. So we start from here. We know that if we did not have this associative edges, we had a collection of chains, we can solve the problem exactly. And if we similarly, if we ignore the adjacent edges and if we just had these associative edges, we can solve the problem exactly, but not with the 2 together. So what we said is actually you should be treating this as a cluster propagation algorithm. So we put it in the framework of belief propagation, but belief propagation where the scheduling happens at a meta level, at a higher level. So you create this cluster graph where your clusters are kind of super nodes which correspond to chains where you know how to do exact inference, or to cliques. So these are cliques which contain only associative edges, and even here you know how to do exact inference, at least for the case where the number of labels is 2, but for other cases also we can design efficient algorithms with approximation guarantees, as I will be coming to shortly. Now once you create this kind of a meta graph, then you could just put it in the framework of belief propagation, where for each node you send a message to its neighboring node on the best possible labelings score you would get for each possible label of the neighboring vertices. Okay, so this is actually, I guess, for this part, if you know what belief propagation, the main steps of belief propagation in a cluster graph, then you will realize that the 2 inference problems that you have to be able to solve is this: that for each chain you want to find the best possible labeling of the nodes in the chain for each possible label of the shared vertex when you have to send a message from a chain to a clique. Similarly, from a clique, when you have to send a message to a chain, you have to find the best possible labeling of all the vertices in the chain for all fixed labels of the neighboring shared vertex. Now for chains, this is an efficient inference algorithm which we have already gone over, but when you have arbitrary cliques, this becomes difficult. Okay? And we will see that actually one can design good combinatorial algorithms, which was not possible earlier when if you just restrict it to standard belief propagation kind of frameworks. So now the problem that you have to solve for within each click, let's just abstract it as follows. What you have when you look at each click with say n nodes, and where each of these n nodes can be assigned one of m possible labels, is a set of two criteria. You have for each node its own preference for the label that it wants. Okay, so each node has a particular score attached to whether it should be labeled as location or person name, organization name, or none of the above. Similarly though, for the entire click you have a score which if you were to handle in the normal framework totally puts you in the NP complete space. But the click scores have a particular property that they are associative, and also the fact that the click scores are kind of symmetric in the sense that the scores are such that if I have a set of 100 nodes, the scores just care about what fraction of them are labeled location and person name and organization, and they don't care about which of the 100 nodes are labeled location or person name or organization. That's the property of a symmetric function. The order of the arguments doesn't matter, okay, for these kind of graphs. And because of this, you can actually design algorithms which do not even depend on the number of edges in the graph. So there is an algorithm that we designed which runs in order nm log n time, where n is the number of nodes in the click and m is the number of labels that you can assign to the click. So this can be actually in practice much better, given when you are scanning long documents. You could often find words which appear say 100 times, and then this pays off a lot. So I just wanted to give you a flavor of the kind of inference algorithms that you might have to design when you try to apply structured models for information extraction. And for more details, this work appears in ICML 2007 conference. You can look up the algorithm. And next I wanted to go into training. But if you have any questions, I can take that now.
So have you applied this to big documents, and roughly how long does it take?
So actually this one is, so suppose if we apply the sequential model, if it takes say some time x, with this one it takes 3x. Whereas if we were to apply belief propagation, it could take 10x, 50x, of course, depends on the size of clicks. Okay. So this training part, it's a kind of a total gear switch. So here we are in this situation where we are given n correct input-output pairs. So you might be given n examples of sentences and their correct vector of predictions, or n examples of sentences, sentence pairs and the correct alignment. The y of course can be anything. And because we are in this structured world, we don't assume that for all possible y's you have the same error. There are some y's which are more correct than other y's. So in general, the user in structured learning typically wants to specify his or her own error function. So the error function for any input I will take as argument the prediction that you are making y and output a real value. So a very typical error function, say for the case where your output y is a vector of prediction, is a Hamming error. So the Hamming error tells you the number of positions in which the correct output yi for the ith example differs from what you are trying to predict y. So let's assume that you are given this kind of an error function and you are given this couplings of correct input-output pairs. And in the training case, you want to find the W for which the error is minimized on the training data, but of course you are only interested in those W's which will generalize to unseen instances. And for structured learning, we want to do this efficiently while being able to handle the fact that for any given x there can be exponentially many possible y's. So that is the main challenge. And for standard single predictions, for example, support vector machines, because they give you a margin between the correct class and the incorrect class, have been shown to generalize very well. So in the last 5 years, people have come up with extensions of the support vector machine kind of paradigm to structured models. These are called max margin trainers. And the basic philosophy of max margin trainers is as follows. Your goal is to come up with a W which will make sure that for each I, the correct yi, the correct outputs score, which is the dot product of the weight vector and the feature vector, is greater than equal to the feature vector times the weight vector score of any other incorrect y. But you want to ensure a margin. It's not just enough to be greater, you want to make sure that it is greater than equal to a margin which is proportional to the error of that output. So things which have large error should be proportionately that far away from the correct output. This is what you would like to do for structured prediction. But this is the hard margin case. Like in the case of SVM, you want to soften it, and the way to soften it is by adding a slack variable. So you add this slack variable, which for each example I, you add this psi I slack variable. These psi i's have to be greater than 0, and you want to minimize the slack. You want over all examples the sum of the slacks to be as small as possible. But of course you don't want to overfit on the examples, so you also add this regularization term, which is the norm of the W. So this has been found to generalize well, and for two reasons. First, because you add the regularizer, and second, because you ensure this margin. Now this is a quadratic optimization problem, and you could go ahead and just solve it using a QP solver, but there is one catch, and that is that the number of possible such constraints you could have is proportional to the number of incorrect y's, and that could be exponential in the number of in the length of the input. So this is one problem, but so that we will come to later. But the other issue, unlike when you do single class prediction, for structured prediction, it's not very clear whether it does make sense all the time to ensure this margin which is proportional to the error of the output. Is that the only possible way in which you should be ensuring generalizability or putting a margin? What other alternatives make sense? So in 2005, there was this piece of work by Sokandiritis, Thorsten Joachims, and a few other people, where they said that another formulation of structured training, which makes also a lot of sense, is to ask for a margin. Like there we asked that each correct input-output pair should be separated from all others by a margin which is proportional to the error. But in this slack scaling approach, we claim that this error-based margin is too large. You don't need this. You just ensure that there is a margin of 1, like in conventional SVM. Just make sure that all the incorrect ones are just a distance of 1 away from the correct one. But then, since you will not be able to meet this requirement exactly, you allow for the soft slackness, and this slack variable though is penalized in proportion to the error. This makes sure that if there is some incorrect y which gets within this margin of 1, just add a penalty which is proportional to the error of that incorrect y. So here then you are scaling the slack variable, the psi I, instead of scaling the margin, which is what you do in the first case. Now this change of the objective actually is more sensible. I will show you numbers which say that in this other method where you ask for a margin which is proportional to the error is asking for too much. You don't need this for training. Solve the simplest problem that needs to be solved. That's the philosophy one should follow for training machine learning problem. It's solving more than that is required, and therefore sometimes it might be cutting corners and compromising something else which is more demanding and important to solve for. So this is, so in the rest of this talk, we will both be worrying about what are sensible formulations for structure training, and we want to do this while still maintaining tractability. We have to respect the fact that the space of possible y's is exponential in the number of inputs. So first, now let's go back to the computation concern. So this is, otherwise it is a QP ready to be solved by a QP solver, except that the number of possible constraints is exponential in the number of, is in the length of the input. So, when the people have come up with a solution to this approach, it's a well understood concept in optimization theory, which is to use cutting plane. You don't put all the constraints at a time. Start with no constraints and solve this QP, you get some value of W. Find out the constraint which is most violated with your current W. Add that, resolve your QP with now your new set of constraints. You will get a different W. And do this iteratively until you find no violating constraint. And this is probably correct. Right? So this is the way to tackle the exponentiality. So now when you apply it for structured learning, to find, so the most important thing to be able to solve efficiently is to find the most violating constraint. So these two kinds of formulation give rise to two different optimization problems to be solved in the structured part. So when you do margin scaling, the first approach of doing training, you have to find the y for which the score plus the error is maximum. Now, you can do this efficiently only when both the feature vector and the error function decompose over the input y. Otherwise, again, you are left with enumerating exponential possibilities. And like, for example, if the error function is Hamming error, you can decompose the error into error at each position of prediction, and then this argmax problem can be solved efficiently. So this is what is used in practice. Everybody uses margin scaling because the inference problem that you have to solve is exactly the same as the inference problem you would have to solve if you just did normal prediction of the structure model. So it easily fits into your infrastructure of inference for structured models. But when you try to use the slack scaling approach, you have to find the most violating constraint, which will correspond to finding the y for which the score minus whatever is your current value of slack at that instance t divided by the error is maximized. Now say the score decomposes over individual parts of y's, and the error function also decomposes over individual parts of y. For this particular argmax problem, it still does not give you a decomposition over the entire objective. Okay? You have no tractability. It does not help you that the error function is, say, Hamming error, which is additive over different positions because it's in the denominator. In the previous case, because it was in the numerator, it was nicely additive and you could solve the argmax efficiently. But because it is in the denominator, this cannot be solved efficiently. But we know that this is a better loss function. This actually empirically, I will show you shortly that we get much better results with slack scaling. It's just because of this difficult inference problem, I was just very surprised to find that both of these methods were proposed around the same time and people just stopped talking about slack scaling. Margin scaling is what was used in all structured learning tasks which have been used, which have been written in the past 3-4 years. There has been a lot of work on coming up with better optimizer, different formulations, different algorithms, but no one has kind of visited this issue of whether this is the right training objective or not. So here are results from two information extraction scenarios. One where we are casting it as a sequence labeling problem, and second where we are casting it as a segmentation problem. These are 3 data sets. This is a data set where we try to extract address elements like city names, area names and road names from address strings, unstructured address string. The second is the citation domain, where given citations from computer science papers, we want to break it up into author names and titles and conference names, year and so on. So this was kind of released in UMass, and this one is a very well-known CONL data set from the Muck competitions. Sorry, not the Muck competition, it's a standalone different competition. And on the y-axis, we are plotting the span F1 error, which means 100 minus the F1 accuracy. So lower values are better. The blue lines are with the margin scaling objective, and the red bars are with the slack scaling objective, and of course slack is much better than margin scaling. For segmentation tasks you don't see much of a difference, but definitely for sequence labeling you see a lot of improvement with using slack scaling. So I'm just telling you that slack scaling is a better, more sensible objective. It's just that because the inference problem is so difficult, it kind of vanished from the literature. So this first contribution of ours is to show that the slack inference problem can actually be approximated very well. You should not give it up so soon. And there is a very simple way of approximating it, which also is theoretically sound, which will give you the benefit of slack scaling without paying the performance penalty. So recall that in slack scaling, in order to solve the optimization problem using cutting plane, we have to find the y for which the score minus this inverse of the error function is maximized. And our pain was that the decomposability of the error function did not help us in solving this maximization problem efficiently. Okay. So the first observation is that the part which is paining us is actually not that bad, in the sense that this part, which is the inverse minus of the inverse of the error function, is actually concave in the denominator. It's concave in EY. And because of that, you could use variational methods to rewrite this as a linear function as follows. So this particular function is equal to the minimization over all possible lambdas. Lambda is a scalar value, all positive lambdas if you went over, and you took this linear combination of the lambda and the error and minus this part, which the most notable part about that other part is that it does not depend on y. Okay. So when you do this approximation, you can actually solve the outer maximization problem more efficiently, but just look at the nature of the approximation. On the x-axis here, I am plotting error of y. On the y-axis is our difficult function, which is minus of the inverse of the error function. And this blue line is what we are trying to approximate. So this is a concave function, as you can see. So instead of trying to find, the best y based on this concave function, what we will do is approximate this concave function by a collection of lines derived from choosing different values of lambda for this right-hand side function. For any possible lambdas, for every error function, there is one lambda for which it will be exactly equal. But if you pick some other lambda also, the right-hand side function will always be above this concave function. Now this gives you an upper bound. It not only gives you an approximation, it gives you an approximate upper bound. So here is how we finally approximate the slack inference problem. So our goal was to find the y. We have exponentially possible, many possible y's, for which the sum of the slack minus this function, which is the inverse of the error function, is maximized. So this is equal to this by the variational approximation. We have not gone into derivation of that, but this is not too difficult to see. And now if you interchange the max and the min, you get this inequality, that this is actually less than equal to min over different lambdas. And now once you have picked a lambda, you can just find the max of this function. Now there are two very useful properties of this approximation. So instead of solving this maximization problem, I will be solving this min-max problem. I do first a maximization after picking a value of lambda, and then I will search over the all possible lambdas. There are two properties. One is that the inner maximization problem is now very nice. It is linear in It uses the error function and the lambdas in a linear way, and if the error function and the score function decompose the same way, you can solve this maximization problem using the same kind of inference problem algorithm that is used for margin scaling. That is one good thing. And the second good thing is that the inner maximization problem is convex in lambda. If the inner maximization problem is convex in lambda, for all possible lambdas you have a convex function, and you can search through the minimum of a convex function is easy to find using golden search. Okay. So we use a golden search technique to find the best possible lambda. And now this gives us a good approximation of slack inference. So these are some numbers on the same data set. So slack inference, it just so happened that for information extraction, sequence labeling and segmentation tasks, we could solve for the optimal slack inference exactly by using an expensive quadratic algorithm. But for all possible tasks, it's not even possible to use slack inference. Like if I wanted to use this for dependency parsing or for alignment, I cannot solve for slack inference. So in such cases, though, approximate slack is totally feasible, and it approximates in terms of accuracy. If you see, it is very close to the slack. In fact, in some cases, it's even slightly better. So in all of these 5 cases, you see it's a good way to reach the slack accuracy without paying the penalty of inference.
Sorry, which one was the approximate?
The one where you, yeah, the min-max problem. So the min-max is
it's
much
approximate just because of the search over lambda.
Yes, no, not because of the search over lambda, because we interchange the min and the max.
Oh, you're just using the.
See, that is the thing. This would be exact, but because we interchange the min and the max, it becomes approximate.
And we don't know the gap.
Yeah, we don't know the gap. But there is a bad news. The bad news is that it's not guaranteed to actually give you the correct implementation of the cutting plane algorithm based on the slack objective. In the sense that you might have a scenario where no lambda can find you a violating constraint even though a violating constraint exists. It's not a problem of discretization. It's a problem of impossibility. You cannot, there may not be any y which will make the violating y the highest scoring in terms of the sum of slack plus lambda times error function. So this is a counter example. Will not go well. Okay. It works well in practice, but it is not guaranteed to be correct, and I was not even hoping it to be, guaranteed to be correct. It just seems to do the job well, and it is a kind of a tractable function now. And then that led us in thinking, what is so sacrosanct about slack scaling? It was one of 2 methods which was proposed by people who are actually optimization people. They don't care about information extraction or structured learning application as much as I thought I did. Okay, and I still do. So then I thought there's got to be a different objective, which is just, it has to be naturally more tractable, and it has to be a better error function, and we came up with something better. So actually, if you think about it, suppose if I created an artificial problem as follows. I took, say you have 1 million prediction tasks to make. They are all independent of each other. And I just arbitrarily concatenate them, and I create an artificial structured learning problem out of it. The features don't couple the y's at all. A good objective should do no worse than solving the million independent prediction problem independently. Otherwise, there is something wrong. And that is indeed the case. When you use slack scaling, you would still just ask for a margin of 1, even though you have 1 million independent predictions. So I just artificially created a vector of 1 million predictors. And because I always ask in slack scaling a margin of 1 independent of the length of the output that I am predicting, I am asking for too little in slack scaling. In fact, in such cases, there was a paper of Thorsten Joachims in KDD 2006 where they showed that you can formulate even independent classification problem as a structured classification problem by artificially concatenating examples. And they are equivalent, and they will in fact turn out to be the same as margin scaling. So in this artificial scenario of concatenating examples and creating one structured prediction, you can in fact argue that margin scaling is better than slack scaling. But margin scaling is not good when you are actually solving a truly structured task, because then it's asking for too much. Margin scaling is overfitting the task and slack scaling is underfitting. It's asking for too little margin. So we actually came up with a different loss function. I'll skip this example, just directly go to this new formulation that we have, which claims that in fact this is what you should be asking for. For every correct input-output pair, you should want a margin of 1, but you should, the slack should be separate for separate error positions. So I am considering scenarios in which the error function, say, decomposes over these parts which I am denoting as C. So in normal, so just to make it comparison easy, this is the slack objective. In slack objective, you have one slack variable over the entire example, entire instance. For each instance I, you have a single slack objective. Here what I am claiming is that you should have for each possible part, for each possible position over which the error decomposes, have a different slack variable. And then ask for this margin of 1 to be applied over all y's which does not agree in the cth position with the correct y. So this is what he's saying. For the ith example, in the cth position, whenever a y disagrees, you require this margin. And by using this alternative loss function, actually you get a much simpler inference problem and much higher accuracy. And there is this notion of coverage which I have used to argue that actually it is in fact more sensible. And here are the final numbers. So this last set is the new objective, which the inference problem is easier, gives higher accuracy. And finally, you see even for segmentation tasks, you get a significant drop in error by using this new training objective, and I'm done.
Why was that an easier inference problem?
Yes, yeah, that was my question. See here, what happens is, you need to find so you fix, say, a C, position C, like when you are doing Hamming error, you fixed, say, the 5th position, and you want over all possible y's which disagree in the 5th position, the y which has the highest score. You can ignore this error, because the error is just tied to that position. So the error does not appear. It's a standard then prediction problem. So in fact, you just, if you want to do this simultaneously over all positions, you find the max marginals in Markov.
Any other questions? Okay, thanks.